So in elementary school, we learned the dreaded long division process. And to remind you how it works, we're dividing 27 into 8,748. We first look at 87 and ask how many times does 27 go into 87. The answer is 3. 3 times 27 is 81. You subtract, and you, as they say, bring down. Then you answer the question, how many times does 27 go into 64? 27 times 2 is 54. That's as close as we can get. We subtract. We bring down the 8. And finally, how many times does 27 go into 108? The answer is 4 times. 4 times 27 is actually equal to 108. No remaining. So we learned this method back in whatever grade, and it's very cryptic. All these numbers, what do they all mean? I feel like in math, this is maybe the first topic that people sort of give up on trying to understand math. So I'm going to just show you a couple of ideas related to long division. Here's another approach to long division. To do 8748 divided by 27. Well, a very, very lengthy way of answering this question would be to just subtract 27, sort of count, let's count it 1, subtract 27, again, count 2, and keep doing that until eventually I get down to 0, or I can't subtract any more 27s. And the number of times I subtracted away 27 would be the number of times that 27 goes into 8,748. Well, that method's not practical, considering the answer is 324. I'd have to do 324 subtractions. So here's a second approach. On the side, I'm going to say, well, 27 times 1 is 27. 27 times 10 is 270. And 27 times 100 is 2,700. 27 times 1,000 is 27,000. That's already bigger than 8,748. So the answer is somewhere between 100 and 1,000. So what I could do is subtract 2,700, which is really 100 times 27. And when I subtract that, I get 8,406. And that's still bigger than 2,700, so I could subtract away another 2,700. $33.48. I just took away another 127. So I just saved myself a lot of work. This 3348 is the result of subtracting away 27 200 times. But I could still take away another 127s. And I end up with 648. So I've taken away 327s. But I still have 648 left. 648 is smaller than 2,700, but it's bigger than 270. So from the 648, I can subtract away 270 to get 378. That 270 is 10 times 27. I could take away another 270, which is another, this is 378. Take away another 270, which is another 10 times 27, to end up with 108. So now I've taken away 320 27s. I still have some stuff left over, so I'm going to start subtracting away just individual 27s. 81, 54, 27, 0. I just took away 4 more. So I took away 327s, 20 more 27s, 4 more 27s, or 324. So that method might seem to make sense. And when I go back to the long division process now, I'm going to show you how it pretty much does the same thing. Basically, when we say 27 into 87 is 3, we're basically saying that 300 times 27 is 8100, and I subtract, and I get 648. Notice how much this looks like this. The only difference is I didn't bring down the 8 also, but I could have. That 64 was really like a 648, and this 81 is really kind of like 8100. But I want to, 648 is too big of a remainder, so now I want to start taking, see how many times 27 goes into 648. Well, 27 goes into 64 twice, which means 27 goes into 640 20 times, and I get to adjust this answer. Turns to 320. So I need to subtract away 20 more 27s, which is 54, but it's really 540, and subtract and get 108. So I have to take away now, we're down to the last digit. 27 goes into 108 4 times. I need to subtract away 4 more 27s. And that's what the long division looks like. If I just were to not show these 2 zeros or this 8 when we bring down the 4, really we're bringing down the 48. I just get rid of those numbers. Literally, I'll erase them. Turns into the long division process. So I hope that shows you why long division works a little bit better than maybe you understood it back when you might have learned it as a kid.